Welcome to Study Loop.
This is the answer to Chapter 22, problem number 39 from the Smith Organic Chemistry textbook. This problem asks us which ester, C or D, is more reactive in nucleophilic acyl substitution, and we are asked to explain our reasoning. Okay, and so I guess I didn't label them, and I probably should. So this is C on the left, and this is D on the right. And with regards to which is more reactive in nucleophilic acyl substitution, so C has an electron withdrawing group, and D has an electron donating group. And so C is going to be more reactive than D. So C is more reactive than D. Oh, not sure what happened there. C is more reactive. Okay, C is more reactive. And basically, to figure out why, we need to look at what the leaving group in these molecules is going to look like. And so basically, if we were to do the substitution reaction, we would end up with this as our leaving group. And then actually, let me draw this out. Okay, so we would have 3 lone pairs and a negative charge on this oxygen. And then the way that we draw the NO2 group is to draw one oxygen with a single bond and the other with a double bond and a positive charge on the nitrogen. And so that is going to look like this. So 3 lone pairs and a negative charge on this oxygen with only 2 and no charge, and a positive charge on the nitrogen. And so we can draw a resonance structure here that's going to look like this. Okay, so the nitrogen is still going to have 4 bonds and a positive charge. And now both of these oxygens are going to have negative charges. This oxygen is now not charged. And basically, this resonance structure allows us to delocalize that negative charge across the NO2 group. And so this serves to stabilize the leaving group here. And when we make a comparison to what we would see in the case of molecule D, what we would see would be this. Oh my goodness. Suffering some serious lag here. I apologize. Okay, so negative charge there. This oxygen uncharged and with 2 lone pairs. And the only resonance structure that we can draw here is going to involve a lone pair here, adding in these electrons moving like this, and these electrons moving to here. And so our resonance structure actually serves to destabilize this molecule because we end up, as you'll see in a moment when I finish drawing it, with two negative charges right next to one another. My Google Chrome is not responding. So I'm going to give this one more minute and then let's see. Okay, there we go. Yeah. Okay, there we go. Sorry about that. Still getting some terrible lag. Okay, but so anyway, this would be our resonance structure that we could draw. So this oxygen is still gonna have a negative charge on it. And now we have a lone pair on this carbon that the oxygen is attached to, and that is going to have a lone pair and a negative charge on it as well. And so that certainly does not serve to stabilize the molecule, and we've added a positive charge to this oxygen over here. And so the presence of those two negative charges right next to each other is going to be super destabilizing. Whereas in molecule C, like I said, we can delocalize the negative charge on that oxygen across the NO2 group, and that is a stabilizing effect. And so that is the reason that C is more reactive than D. And that's the answer to chapter 22, problem number 39.